Welcome to this explainer. Today, we're embarking on a pretty amazing journey. I mean, we all kind of understand the basics of electricity, right? But mapping its exact physical path from the raw, massive power of a distant station all the way down into the very circuitry of the living room you're probably sitting in right now, well, it reveals an absolutely incredible feat of engineering. So let's track that current.
It's a super simple action. You flip a switch and boom, you get light. But the sheer physics and honestly the intricate safety systems operating right behind your drywall, the literal second you make that connection, is just astounding. Today, we're going to demystify exactly how these incredibly dangerous forces are safely, flawlessly routed through your home.
Okay, let's dive into this. Here's our roadmap for today. We'll be looking at 1. From grid to your home. 2. Entering the property. 3. Inside the consumer unit. 4. The safety gatekeepers. And finally, 5. The critical earth wire. All right, kicking things off with stage 1, from grid to your home. So before the electricity even leaves the plant, we need to establish exactly what kind of power is being sent out. The power station generates alternating current, or AC. This is current that constantly reverses its direction. And you might be wondering, why AC instead of direct current, or DC? Well, it really just comes down to sheer physics and economics. AC is vastly more efficient when you need to distribute energy over the massive distances between a power plant and your local town. Let's move to and see how this builds. Imagine this massive electrical highway. The current leaves the power station and instantly hits a step-up transformer. This thing cranks the voltage way, way up, so the electricity can travel over those giant long-distance transmission lines without losing too much energy along the way. Once it finally reaches your town, it hits a substation. Here, a step-down transformer reduces that crazy high voltage into something much safer. Finally, it's routed through local distribution cables, which might be strung overhead on poles or buried deep underground, right to your very street. Now, electricity is actually distributed through local streets in 3 phases. But unless you're running a massive industrial factory or, maybe a secret supervillain lair, your home is what we call single phase. That simply means your property taps into just one of those 3 main distribution phases, along with a neutral wire. And to keep the local transformer perfectly balanced, the electricity supplier will cleverly alternate homes right down the street. So your house gets phase 1, your neighbor gets phase 2, the next house gets phase 3, and so on. Pretty smart, right? Moving right along to stage 2, entering the property. So, the physical bridge between the street and your actual house is called the service cable. Arriving either from a pole up above or a trench down below, this specific cable carries that dangerous raw power right to your doorstep via those phase and neutral wires we just talked about. And because there is an incredible amount of energy packed inside, these wires are securely wrapped in a tough metal protective sheath to prevent any accidental damage. So the crucial point is exactly what happens the moment this power hits your house. Let's trace that sequence. First, it hits the service fuse. This is the absolute ultimate gatekeeper for the whole property. It physically limits the incoming current to a safe level, usually somewhere between 60 and 100 amps. Interestingly enough, distribution companies can physically pull this fuse entirely out to completely 100% isolate your property from the grid. After that, the current flows into the electricity meter, which meticulously quantifies the energy you're consuming for your monthly bill. And finally, it flows right into the consumer unit. And that is where the real distribution magic happens. Which brings us to stage 3, inside the consumer unit. You probably just call it your fuse board. The very first component the electricity encounters inside this box is the main switch. This is a manual double-pole isolation switch, and it's really vital to remember that this is a manual override, not an automatic one. If you ever need to completely kill the power to your entire property for, say, a major repair, you physically pull this switch. By being a double-pole switch, it guarantees that both the incoming live phase line and the outgoing neutral line are completely disconnected at the exact same time. Now for the most critical part, stage 4, the safety gatekeepers. To understand how these gatekeepers actually work, we really have to establish a foundational concept here: balance. Electricity operates on a super strict loop. The phase line brings the electrical current into a circuit, and the neutral line provides the exact, identical return path back out to the grid. Put simply, whatever amount of current flows in through the phase wire absolutely must flow back out through the neutral wire. No exceptions. And this brilliantly illustrates the difference between the 2 main types of automatic switches sitting on your fuse board, the RCD and the MCB.
They literally live right next to each other on a conductive metal bar called a bus bar, but they do entirely different jobs. The RCD, or residual current device, well, its core job is to protect human life. It constantly monitors that delicate balance of current flowing in and out. The MCB, or miniature circuit breaker, on the other hand, is there to protect the property itself. It's what stops your wiring and equipment from melting or catching fire.
The sensitivity of the RCD is honestly staggering, just 30 milliamps. If an RCD detects a difference of just 30 milliamps between the current coming in and the current going out, it interprets this missing current as an extreme danger. Why? Well, because that tiny bit of missing current might very well be flowing through a human being and into the ground.
Think of the RCD as a perfectly, meticulously balanced accounting scale. It is constantly weighing the phase against the neutral. Let's say you accidentally touch a live wire. Suddenly, electricity flows through you instead of the neutral return wire. The scale tips. The RCD instantly detects that the current isn't perfectly equal anymore, and in a literal fraction of a single second, it trips, physically cutting the power. Now, modern homes usually split their circuits across multiple RCDs. That way, a fault in, say, your kitchen toaster doesn't plunge the entire house, upstairs lights and all, into total darkness.
Now, let's look at the MCBs. These guys sit downstream from the RCD. Each MCB controls a specific, smaller circuit, like just the downstairs lighting or the upstairs sockets. Imagine a scenario where you're making breakfast. You gradually plug in a kettle, a microwave, a blender, maybe a space heater, all on your 32-amp kitchen circuit. The wires hidden inside your walls are getting hotter and hotter. But before they can melt and cause a literal house fire, the MCB detects that the 32-amp limit has been breached. It automatically trips and cuts the power to protect that specific circuit from the overload. But the MCB has a second, equally critical function, protecting against short circuits. Imagine a wire frays, and the live phase touches the neutral wire directly. That completely bypasses the appliance it was supposed to power. This creates a massive, instantaneous surge in current. This surge is so incredibly fast and so powerful that it generates a strong magnetic field right inside the MCB itself. That magnetic field literally, physically pulls the switch and cuts the power, neutralizing the threat instantly.
Finally, we reach stage 5, the critical earth wire.
If you've ever looked behind a faceplate, you may have noticed those green and yellow striped wires running behind your light switches and plug sockets. This is the earth wire, and it is an absolute lifeline. Let's say a wire inside your washing machine rattles loose and touches the metal casing. If you were to touch that casing, you could get a lethal shock. But because the metal casing is intentionally connected to this green and yellow wire, the rogue electricity instantly flows down the earth wire instead of through you. This massive diversion of current immediately unbalances that RCD scale we talked about earlier, causing it to instantly trip and cut the power. It even connects to the metal, gas, and water pipes in your home just to be extra safe. Now, what's really interesting about this is how that earth wire actually completes its journey to the literal physical ground. The main earthing terminal near your meter has to connect to the earth, and electricity suppliers do this in 3 specific ways. Sometimes they wire it straight into the neutral wire of the incoming service cable. Other times they attach it to that thick metal protection sheet wrapped around the service cable we saw earlier, letting it ride that sheath all the way back to the local transformer. And what if the supplier doesn't provide an earth path at all? Well, then the terminal is wired directly to a long metal electrode rod that is physically driven deep into the dirt right outside your home.
Which brings us to the end of our journey today and to this final question. When you think about it, from the massive step-up transformers at the distant power station, down through those buried service cables, right into the complex fraction-of-a-second balancing acts performed by your RCDs and MCBs, there is an absolute awe-inspiring symphony of engineering happening silently right behind your plaster and drywall. Knowing the incredible journey and knowing about those tireless gatekeepers keeping you safe, will you ever look at a simple light switch the exact same way again? I know I certainly won't. Thank you so much for joining me on this explainer, and hey, stay curious.